You can put me on the live now.
We've started. You
All
can
right.
continue with the discussion.
Yes. Yeah, I'll just start. Uh, Good evening, one and all present here. Hope I'm audible to you. Yes. And hope my screen is visible. Uh, Hello. Am I audible to everybody? Hello. Yeah. Good evening, one and all present here. Uh, I, on behalf of the management, on behalf of the management, principal, HOD department of EC and organizing team, I, Faninder Ravi, welcome you all for the second day of the webinar series on recent trends in real world, organized by Department of Electronics and Communications Engineering, Sir M. Vishweswaraya Institute of Technology, Bengaluru. The topic for today's session is understanding digital image processing, a deep learning perspective. I feel extremely proud and honored to introduce you to today's resource persons. The two people whom we are going to interact with are young technocrats, successful entrepreneurs who chase their passions, made their dreams into reality, and they are backed up by their principles and motivation. At first, let me introduce you to the first guest speaker, Mr. Akash Deep Singh, who is Chief Operating Officer, Tessellate Imaging. Akash earned his BA honors in degree in electronics and instrumentation engineering from BITS Pilani KK Birla Goa campus. He is a tech whiz, passionate about solving real world problems with artificial intelligence and machine vision. He has worked on building novel systems to detect and classify glioma cancer and a camera based real time stat generation solution for basketball players. He was also a part of a team which built India's first panoramic camera, where he acted as a machine learning lead. His past projects include autopilot firmware for search and rescue drones, building disguised and imposter face recognition software, and all-terrain navigation vehicle, and sketch-to-face image matching for forensics. A National Cyber Olympiad gold medalist, and he loves reading books. The second guest speaker for the day is Abhishek Kumar Annamraju, Chief Technical Officer, Tessellate Imaging. Mr. Abhishek is also a BE honors degree holder from Electrical and Electronics Engineering background from BITS Pilani KK Birla Goa campus. Abhishek's research areas include computer vision, machine learning, natural language processing, and photogrammetry. As a part of his undergraduate thesis, and then continued employment at Tata Elxsi R&D India, he worked on-road real-time vehicle detection. He has published research papers on cascade classifiers, shape-based object analysis, and traffic signal classifiers, IET Intelligent Transport System journals. His past projects include image-based monitoring solutions to curb illegal sand mining, 3D facial model detection, model generation and classification, deep learning based face recognition, and camera auto calibration for fisheye images. He was also a part of the Mahendra Rice Challenge 2014 and developed real-time stationary cam object detection modules. He participated in Google's Summer of Code 2016, working with Open Detection to develop GUI-based deep learning training and classification systems. His research work includes projects involving forensic sketch to image matching and biomedical image processing. Before I hand over to the guest speakers to start the session, I like to put on records a deep sense of thanks to Miss Sinchana who made a link possible with tessellate imaging. Hope you'll all enjoy this session. Over to you, speakers.
Thank you, sir, for that wonderful introduction. And I hope the audience has a knowledgeful 1 hour. All right. I hope I'm audible.
Yeah, you're audible.
All right. All right. So today we are gonna go through a little bit of fundamental mathematics of image data, and try to understand how what we learned today can be applied to the machine learning world. Hello, everyone, and welcome to today's webinar. Let's begin. So in computer vision, we may want to know how far away a building is to a camera, whether a vehicle drives in the middle of its lane, how many people are in a scene, or we may even want to recognize a particular person, right? All these questions are to be answered based on recorded images or videos. Areas of application have expanded recently due to a solid progress in computer vision. There are significant advances in camera and computing technologies, but also in theoretical foundations of computer vision methodologies. In recent years, computer vision became a key technology in many fields. For modern consumer products, for example, apps for mobile games, driver assistance for cars, or user interaction with computer games. In industrial automation, computer vision is routinely used for quality or process control. There are significant contributions for the movie industry too. Example, the use of avatars or creation of virtual worlds based on recorded images. In today's webinar, we'll take a look at fundamental mathematics behind image data. We'll try and understand some statistical measures around images. We'll briefly look at how to use this knowledge within the context of machine learning by understanding submodular optimization. Finally, we'll end the session by pondering over a little bit of color perception. Before we begin, let me introduce who I am and what is Tessellate Imaging. So I'm the co-founder and operations head at Tessellate. We've been working last 7 years now, helping businesses set up their computer vision infrastructure. So, right from gathering the right type of data to training complex neural architectures and finally deploying computer vision applications. We've got a chance to work with a broad spectrum of imaging modalities along the way, and we've solved some really crucial and critical bottlenecks of computer vision. All right, let's begin. To begin, let's look at some basic notation and mathematical concepts for describing an image in a regular grid in the spatial domain. A digital image is defined by integrating and sampling continuous data in a spatial domain. It consists of a rectangular array of pixels, each combining a location and a value. These points form a regular grid, and we assume a left-hand coordinate system. In a more formal way, an image is defined on a rectangular set by the carrier function omega by this formula. So there are two ways of thinking about geometric representations of pixels, which are samples in a regularly spaced grid. Images that we see on a screen are composed of homogeneously shaded square cells. Following this given representation, we may think about a pixel as a tiny shaded square. This is what we call the grid cell model. Alternatively, we can also consider each pixel as a grid point value. This is what's known as a grid point model. Pixels are the atomic elements of an image. They do not define particular adjacency relations between pixels per se. In MonkAI, pixel locations are adjacent if and only if they are different, and their tiny shaded squares share an edge. Alternatively, we can assume that they are adjacent if and only if they are different and their tiny shaded squares share at least one point, that is an edge or a corner. A window within an image is primarily a subimage. So for an original image of say size m cross n, a window could be a smaller subimage with an odd dimension. So usually a subimage has a dimension which is odd in number, and both height and width are equal for the subimage. Image values are taken in a discrete set of possible values. It is also common in computer vision to consider the real interval between 0 to 1 as the range of a scalar image. If 8 bits are used, to represent an image within computational systems, the scalar image will have integer values from 0 to a max of 2 raised to the power a whole minus 1, which will be, for the case of 8 bits, this will be 255. It is common to identify such scalar values with gray levels, where 0 represents a black and 255 represents a white. All the other gray levels are linearly interpolated between black and white. We speak about gray level images in this case. For many years, it was common to use 8 bits for image representation. Recently, 16 bits became the new technological standard. On the other hand, a binary image has only two values at its pixels, traditionally denoted by 0, which represents white, and 1, which represents black, meaning black objects on a white background. In contrast with this, a vector-valued image has more than one channel or band, as it is the case for scalar images. Image values are vectors, with the length being the number of channels. For example, color image in the common RGB color model have three channels, one for the red component, one for the green, and one for the blue component. The values in each channel are in the range of 0 to the power a minus 1, where a denotes the number of bits used to represent the image. So each channel is basically just a gray level image. Assume a scalar image, and just by following some basic statistics, we define the mean, which represents the average gray level, and the variance of image as follows. The root of variance is the standard deviation of the image. A histogram represents tabulated frequencies, typically by using bars in a graphical diagram. Histograms are used for representing value frequencies of a scalar image, or of one channel or band of a vector-valued image. Here in this example, the plot below each image represents the frequency count for every pixel value. The left image is underexposed, with most of the pixels within the image being on the lower range. Whereas for image on the right, which is overexposed, most of the pixels carry values in the higher range. The middle image is said to be well exposed, with a sort of uniform distribution in pixel values across the whole range. In image analysis, we have to classify windows or subimages into categories, such as within a homogeneous region, or of low contrast, or showing an edge between two different regions, or maybe of high contrast. A three-dimensional view of the gray levels, here interpreted as elevations, illustrates the different degrees of homogeneity in an image. The steep slope from a lower plateau to a higher plateau is a typical representation of an edge in the image. The basic statistical definitions already allow us to define functions that describe images, such as row by row in a single image, or frame by frame for a given sequence of images. When considering image data in a new application domain, it is also very informative to visualize intensity profiles defined by 1D cuts through the given scalar database. This sets training intensity profiles along the x-axis of the shown gray level image. Again, we can use mean, variance, and histograms of such selected narrow windows for obtaining an impression about the distribution of image values. Histograms or intensity profiles are examples for spatial value statistics. For example, intensity profile for all rows in one image define a sequence of discrete functions, which can be compared with the corresponding sequence of another image. Now, suppose we wish to carry out normalization of one function with respect to another. How do we go about it? So suppose let mu and sigma be the mean and standard deviation of a function. And suppose we are given two real valued functions f and g with the same discrete domain and non-zero variances. If we define alpha and beta to be as follows, then the function g nu has the same mean and variance as the function f and is the normalized version of function g. To define the distance between two real valued functions, we use the standard formula, which I'm sure you already know. These are also known as the L1 and L2 norms. Now, assume two different spatial or temporal data measures denoted by f and g. We first map g into g nu, or formally called normalized version of g, as we saw earlier, such that both measures now have identical mean and variance. Now, what we can do is we can calculate the distance between f and g nu using either the L1 or L2 metrics. The two measures f and g are said to be structurally similar if and only if the resulting distance between f and g nu is close to zero. Structurally similar measures take their local maxima or minima at about the same arguments. Now let's take a look at how we can use what we've learned in theory and apply this to machine learning. Along the way, we'll try and understand what submodular optimization means. I'm sure that most of you don't know what that is, and if you don't know what that is, it's going to be okay. This is going to be mostly a high-level overview of what you can do with submodular optimization and why you might want to do that. So the big problem that we are facing today is the fact that data sets have been getting increasingly big, especially in computer vision. These large data sets are good because when you have more data, you cover more modalities of the data that you might care about. For example, if you're producing an image recognition system, you might want to see images of, say, a dog in different positions, in different lighting conditions, so that you might be able to better recognize it in the real world. So that's great, right? But then there are also downsides that typically arise. What happens as you increase the size of your data set is that you also increase the data redundancy. In your data set, maybe we don't really need, say 14 million images to be able to capture the core essence of what's going on. A few papers have come out recently showing that the popular CIFAR 10 and CIFAR 100 datasets, where not only do you have redundancy in the dataset, but that you also have exact duplicates in your training and your test set. The research paper talks about how this can cause over-optimistic assessments of how well your model performs. So in addition to these exact duplicates, there are also near duplicates, which are almost the same or at times very similar. Now, the question really arises, do those really count as different examples? Well, what you care about is not necessarily data redundancy between your training and your test set, which is kind of a philosophical question. The important thing here is that you have a giant training set and you want to reduce it down to a more manageable set. So if you look at some samples, these are pretty similar images. Now, the question arises whether these do help your model in learning the object better, or these act as redundant samples, right? So There are different similarities that can be taken into account. There could be pose, there could be color, there could be similar backgrounds, or in fact, similar color and textures. When you're trying to reduce your training set to reach a more manageable size, so that has a lot of applications. I mean, if you have some large data set which you can still compute on, you might not want to do things like, hyperparameter selection on it, because it'll take tons of time for just, maybe basic data explorations. So you might want to reduce it down to something that you can operate on a lot faster. There are other massive data sets that you simply can't compute on. Examples of domains that face these issues would be satellite imagery, or sky captures for astronomy, or maybe ADAS systems. So something that you might want to do is say, okay, many of these pictures are very similar to each other because they are taken sequentially. What ideally we'd like to do is reduce it down to the frames that contain most different set of information on them, and build our models and do our analysis on just those. So in machine learning, we are trying to optimize all the weights in our model by doing convex optimization approaches. I mean, we are trying to tune our weights in our model to get the best performance, and our convex optimization efforts get us there. In contrast, submodular functions operate on sets. They tell you how good a particular set is, and by optimizing a submodular function, you're choosing the best subset out of the larger data set. There are a variety of contexts in which you might want to do this. So a new software package called Apricot, released back in just 2019, focuses on submodular optimization, with the purpose being for machine learning application. Uh, if you get a chance, feel free to check this out. Now, Apricot focuses on the scenario where we have some massive data set and you want to reduce it to a subset that minimizes the redundancy amongst the examples. Submodular functions serve the following purpose. Imagine that you have some big set Y. Now you also have some proper subset of that denoted by X, with all the examples within X that are also available in Y. Now suppose you have some new example. If you try to add that new example to the smaller data set, you are going to get a bigger gain than if you add it to the bigger data set. I hope that makes sense. This formula is the exact representation of that. This makes sense when you're trying to measure redundancy. As you add examples to your data set, any new example is either going to equivalently add variety to the subset or be slightly redundant with any of the new examples that you add. One of the most common submodular functions is called facility location. And this quite literally comes from the task of locating facilities. The problem that companies would have is, suppose, I have many factories in multiple locations within some country, let's say India, and I want to know where should I put my next facility. Well, you want to put your next facility in an underrepresented region of the country that is likely to have many customers that are not currently served by one of your locations. So the way that facility location works is on pairwise similarities, that you take 2 points of data between them, and you want to return a set that is highly similar with as many of the other points in the data set as possible. So there's this equation here that basically says, if you have some big data set Y, which is all your data, and you have some subset X, which is what you're trying to get out, you can evaluate the quality of your subset by saying for each point in Y, what is the maximum similarity to one of your points in X. I mean, I highly appreciate this contribution, and if you're looking to venture further into this topic, feel free to go through this library. The developer has maintained a scikit-learn based API wrapper with the underlying blocks being abstracted away from developers. The library is again highly modular and allows you to create your own similarity metrics to optimizing your own creative modular functions too. With that, I would like to take some time to introduce you to our contributions for enabling computer vision developers in applying deep learning algorithms. Our open source toolkit Monk tries to simplify and abstract the processes of prototyping and training deep neural networks with some really unique and user-friendly features, right from automated exploratory data analysis to comparisons to doing hyperparameter search. Now, MonkAI follows a standard syntax and acts as a low-code wrapper on top of widely used frameworks of PyTorch, Keras, and MXNet. Currently, MonkAI supports two major computer vision algorithms, first being transfer learning based image classification. And on the other hand, we have state-of-the-art object detection workflows wrapped around in a standard workflow. We also have available features for designing and developing custom neural networks, including automated debugging for custom neural networks. Finally, we have a point-and-click interface for engineers and developers who are not that well acquainted with computer vision or deep learning, but still want to build computer vision applications. Now, some of the critical things that we took into consideration before going ahead and building a toolkit was that we wanted to design end-to-end workflows that were focused on what users care about. So having worked in the domain for the past 7 years, we understood the challenges and hassles of what a computer vision developer faces today. And so we try to design end-to-end workflows that helps a computer vision developer build applications faster and quicker. Now, what we've also tried to do is reduce the cognitive load. So if you look at popular frameworks like TensorFlow, PyTorch, Keras, or MXNet, uh, being deep learning libraries, they are intrinsically complex in nature. And having been used for so long, they have reached a complexity that includes both programmatic complexities and mathematical complexities. What we've tried to do is using jargons that domain experts use today, we've tried to follow a standard low-code syntax that abstracts away all the nuances of these frameworks, while still providing you API access to all the core features that are available in these frameworks. Finally, we also try and provide some helpful feedbacks and automations at places where user input isn't actually required. So for example, when you're trying to design your own custom neural network, ideally you don't want to decide the shape or calculate the shape of each layer, right? We do this with Monk automatically so that you don't have to worry about that. So let me describe each of these components briefly and where you can get a few resources if you're looking to begin. So like I mentioned, to begin, we have image classification, and that too transfer learning based image classification. So you have options to create projects, experiments. The dataset formats that this ingests is either using folder datasets or CSV labeled datasets, which is pretty standard in the image classification problems. You can select multitudes of pre-trained deep neural networks from each of the individual frameworks. Now, some unique features are that you can resume experiments wherever you take a break. You can also compare multiple experiments together, not just within the same framework, but also across frameworks too. So if you want to get started with MonkAI, you can take a look at, you can go on GitHub and check out monk_version1 repository. Like I mentioned, we've tried to follow a low-code syntax wherein you can begin your training for image classification in just 4 lines of code. Again, inferring on images is pretty simple, and you can do so in just a single statement. MonkAI right now supports multiple OS platforms with multiple Python versions and CUDA support as well. What we've tried to do, in fact, is prepare a comprehensive set of study roadmaps that you can try going through for understanding both image processing and how you can apply deep learning to computer vision problems. Now, each of these notebooks are in fact independent on their own behalf, in that each of the notebooks that are available within study roadmaps contain instructions right from setting up MonkAI down to inferring on a training on a test image. We've also tried to create an image classification model zoo, where if you're looking to build an application from scratch, ideally we suggest, if any of these examples resemble one of the applications that you're trying to build, you don't necessarily have to, begin from scratch. You can pick any of these models or Jupyter notebooks and start comparing if this solves your purpose or not. If it solves your purpose, that's great. If it doesn't, you can, begin fine tuning this to your purposes, which is what transfer learning is used for. So we have multitudes of applications from different domains. We've provided trained models too. So with object detection, the usual challenge that occurs is that different object detection workflows have different dependencies, different setup instructions, different ways of ingesting labeled data sets. And finally, usually with research object detection workflows, inferring or training on custom data sets isn't really accessible or available. What we've tried to do with Monk object detection is we've wrapped state-of-the-art object detection models and object detection researches in the same low-code syntax that we saw earlier, uh, and we've kept dataset ingestion or custom dataset ingestion very, very easy. Now, there are scripts available with which you can convert dataset formats from one to another. For example, you can, if you're trying to use Coco dataset format, or trying to convert from YOLO to Coco, there are scripts available that you can readily use. Uh, we've also tried to reduce the load that is required for setting up. So we have a single line setup of object detection workflows. Now, just like image classification, we also have an object detection model zoo. And like I described earlier, if you're looking to begin an application from scratch, if any of these applications resemble or are similar to the applications you're looking to build, we have available pre-trained models and the entire Jupyter notebook with using which you can begin. You don't have to begin from scratch. Finally, we have a GUI-based deep learning toolkit, which acts as a point-and-click interface for carrying out or building both image classifiers or object detectors. Now, with the GUI, we've tried to simplify the entire process. So anyone who is not a programmer can also apply deep learning to computer vision and build computer vision models using a point-and-click interface. The entire feature set of tuning hyperparameters to setting the number of epochs and learning rates to selecting optimizers, the entire suite of programmatic access is now accessible also via a GUI. Currently, MonkGUI supports Ubuntu as a platform since it depends on PyQt. We're actively working towards supporting multiple OS environments too. So now let's take a look at what kind of a syntax or workflow do we follow within Monk and how you can build your own image classification systems. And along the way, we'll take a look at some of the unique features that are accessible with Monk and how you can utilize them better. So on Colab, ensure if anyone is following the code along with me, ensure that you select GPU as your runtime. In this example, we are going to be using MXNet Gluon CV as the backend framework. Switching between frameworks is pretty simple and pretty easy. It's just a single line import command. So like I described, each of these notebooks are complete and independent in that they include setup instructions down to training a model and finally inferring on test images. To set up MonkAI, all you have to do is clone it from Git, and depending on the platform that you're using, so right now we are trying to use Colab, you can set up the requirements based on the CUDA version and the platform that you're using. I hope if any one of you has a doubt, they are being cleared by our contributors in the comment section. All right, now that we have set up MonkAI, we can begin with our experimentation. To import, like I described, importing the backend framework is just a single line command. To switch between different frameworks, all you have to do is replace the import command from Gluon prototype to say PyTorch prototype or Keras prototype, and the backend will be selected accordingly. Now, as a deep learning engineer, you ideally would have to, prototype multiple experiments before you can arrive at the best performing model or best performing approaches. So within the framework itself, you are provided with a project and experiment management framework. Now, as soon as you initialize or run this code where you create a project and an experiment, a workspace directory is created. Now, the structure of the workspace directory is that within workspace, you have multiple projects. Within each project, you can have multiple different experiments. The experiments would have their own lists where all training logs for training validation accuracies and compute usage graphs are plotted. There'll be also a model folder. Now, the models folder will include all the intermediate models throughout the epochs and the final and the best performing models too. Now let's quickly take a look at how we can create a binary cat versus dog classifier, which is pretty simple, I'd say. But what we're trying to do here is understand the workflow that we try and follow and keep it uniform across all algorithms. Now the data set structure as described earlier, we either take a CSV labeled file where you have all the images within one image folder, and you have a CSV labels file which contains image IDs and the attached labels for each image. Now with a single line of code, you select the model that you want to use. So right now we are trying to use a pre-trained neural architecture of ResNet 18. You pass the dataset location, so wherever your dataset resides. So right now, since we are using a folder dataset, we just pass the location to that. We also set the number of epochs we want to train this model for. So when we run this, the pre-trained model is downloaded and set. We also get some informative messages. For example, what's the current train val split? How many processes are being used? What's the current batch size and input sizes? What kind of image transforms are being applied to both training and validation sets? We also get statistics about the dataset numbers. And finally, we have some information about the hyperparameters. So what optimizers we are trying to use, what's the learning rate, and if we have a learning rate scheduler, when does the learning rate reduce? What kind of a loss function are we using in this case, right? We also have some system parameters that are available. So in case you do not want to save intermediate models, so for our example, we are doing a training for 5 epochs. If you do not want to save models for, say, the first 4 epochs and just want to save the best performing model and the final model, you can switch this off pretty simply. You also get access to some display runtime parameters that you can turn on and off depending on your comfort. And within just 3 lines of code, you are set to begin training. So as you can see, the training completes. Since this was a very small data set, the training completed really, really fast. And also because we are using a GPU. So the training completed in 6 seconds, and the final best validation accuracy that we received was of 81%. And now we can move on to inferring on a test image. Now to infer on a test image, again, you have to initialize a prototype function. So after you've trained and your final models have generated, you can once again load your project and experiment, and load the experiment setting the eval infer flag to be true. Now suppose you want to evaluate on a folder of images how well does the model perform. Now if you have a validation data set, you can load the validation data set using this. And finally, you can generate class-based accuracies of how well your trained model performs on the validation data set. So as you can see, for the cat class, this performs with 100% accuracy, but for the dog class, it kind of still has a bit to learn. So you get these pretty insightful messages for average accuracies, the total number of images in the validation set, and the number of correct predictions. So now suppose if you want to, evaluate just a single test image, you can again do so. So all you have to do is, with a single line of code, you have to pass the image path, whichever your test image is, and you can run inference on the test image with the trained model. You get, predicted class and predict final score. I hope this workflow appears simpler than most of the widely available frameworks that you utilize. Now, this was a very simple example that I described. There are some really cool, workflows that we have tried describing in our study roadmaps. So, for example, how does changing a certain hyperparameter affect transfer learning, and how can you update or utilize these updates in hyperparameters to make the model go your way. So we have an automated hyperparameter tuning feature available within the library. So for example, if you have a bunch of optimizers or a bunch of learning rates, and you want to explore which of these list of optimizers or batch sizes or learning rates will give you the best performing accuracy, you can do so by running quick experiments on a subset of the entire data set. So once again, you set up MonkAI, you create an experiment, you pass in the dataset path, and when you want to create an analysis or do a hyperparameter search, all that you have to do is pass in a list of hyperparameters that you want to test out, and the percentage of data on which you want to evaluate these learning rates or optimizers or batch sizes. Now, this is a very quick and crude way to find out the best initial hyperparameter state that you want to begin with. However, as deep learning goes, you'd have to ideally experiment more than once to rest upon a final set of hyperparameters that you want to work with. Finally, once you find out the best performing hyperparameter, you can update. So for in our case, we are trying to explore which learning rate performs the best. So we have 5 learning rates that we explored. We get training and validation accuracies printed, and so we find out that a learning rate of 0.01 produces the least validation loss, and so we go ahead with that, so on and so forth. Now this is another feature, a useful feature that is helps reduce the time when you're trying to prototype a deep learning model. We also have certain study roadmaps, Jupyter notebooks that help you analyze the effect of different types of hyperparameters. So for example, when you increase the number of classes in the data set, how does it affect the performance of a deep neural network? Or for example, if you want to explore multiple different neural architectures to find out which one of the pre-trained model works the best for you, you have ready to use notebooks that you can pick up and start experimenting on your own data sets. We've tried to include all the 3 frameworks that are available with MonkAI right now. We are actively working towards integrating more new frameworks as we speak. And I'd say this is a pretty comprehensive and useful resource that our contributors have built, and feel free to check them out. And if you like them, do give us a star on GitHub. Finally, to end today's webinar, I'll briefly talk about the perception of color. And although visual perception appears as a simple process on the surface, we still are perplexed by what goes on inside our head. Now, perceived color is not objectively defined. Color perception varies for people, and it depends on lighting. If there is no light, then there is no color. Just for example, inside a non-transparent body, color can be an important component of given image data, and it is valuable for visualizing information by using false colors. Human vision not only discriminate dozens of gray levels on a screen, but hundreds to thousands of different colors. Humans perceive color differently. Color, in fact, is a psychological phenomenon. But there appears to be an agreement that yellow, red, green, and blue define the four primary color perceptions. In fact, gray levels are not really colors. They are described by the luminescence, the physical intensity, or the brightness, the perceived intensity. A uniform scale of gray levels or intensities is common. In fact, J. Eaton, a Swiss author, wrote a very influential book, The Art of Color, which deals with contrast, saturation, and hue, and how color affects a person's psychology. In brief, he assigned, the following meanings to each of the different colors. In fact, I would like to, end this brief lecture on image data with, a demonstration of how easy it is to trick your brain with optical illusions. And, maybe we can begin to take questions from the audience itself. Well, some of the questions that the audience members asked, is momentum being used to speed up? Well, yes. What we went through today was the quick mode of building a deep learning model. In fact, all the available features within the original frameworks, for example, PyTorch or Keras, is accessible via MonkAI. So if you want to set up momentum, you can do so with our API. So I'd say with that, we can come to an end with today's webinar. I would like to thank everyone in the audience for their participation, and look forward to sharing more bits of knowledge going ahead. Thank you once again to the organizers for helping us set up a platform to impart education on these intrinsically complex topics. And finally, thanks to our contributors and future interns of MonkAI. We are actively looking for interns and contributors to work with us in developing a standard workflow for computer vision. Of course, right now there are multiple heuristics or approaches with which you can solve an individual computer vision problem. What we are trying to achieve is reduce the chaos when trying to solve a computer vision problem by standardizing the workflows and accessible features for developers. I thank you and wish you all the best for your endeavors that you're working towards. I guess I can hand it over to Ravi.
Yeah, thanks, Akash. If you have any doubts, probably we can take some doubts. You can. There were a lot of doubts which Abhishek is answering online anyway. You can explain them some of the things if you want for another couple of minutes.
Sure, sure.
Yeah.
But I guess Abhishek has answered most of the questions that were asked throughout the
Yeah.
lecture.
Yeah. Yeah.
So we are actively looking for interns, like I mentioned. And if you want to work towards Monk and with Monk, feel free to approach us. We are accessible via all social media channels on LinkedIn or email. And just push us a message of if you're working towards a cool computer vision application, or maybe you just want to learn something new and are getting introduced to the topic of computer vision and image processing. Feel free to reach out to us, and we would love to help go a long way.
Okay. Okay. So if that is the end, then yeah, I would like to thank our HOD, Dr. Sundar Guru sir, for supporting all us. And on behalf of the organizing team, I take this opportunity to thank Akash and Abhishek from Tessellate Imaging for handling this session. And yeah, it was a very good learn for the time what we had. It was a good introduction. Thanks a lot. Thanks a lot for your sharing your technical knowledge. Then yeah, I thank all the participants who have patiently waited and listened to that. Hope this session was useful for you, and you have a little bit of you have developed a little bit of insight as how Monk AI helps you out in easing your process of neural network building for image classification, or any kind of, or developing a neural network AI solution for your problem. There's a lot of things which we can learn, which Akash has given introduction to us. So hope you have enjoyed this session. Thanks a lot for joining us today. And tomorrow we'll have the concluding session, the last session at 7 o'clock sharp. And yeah, towards the end of tomorrow's session, we'll be spreading across the feedback session, feedback, and once the feedback is done, we'll be in the process of processing your certificates and all. Thank you. Thanks a lot for joining. That's all from my side. Good night, everybody.
Thank you, everyone. Good night. Take care. Stay safe. Stay healthy. Bye bye.